New paper for diffusion models is actually quite a good idea to make diffusion models faster. In diffusion models, we have a sentence. The capital of France is mask, 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 mask. So let's say in this case, we want to predict letters, Paris. In the first iteration, it can predict P-A-R-U-S. In the next iteration, it can find that this U is low confidence, so predict, so mask it again, and then try something else, I. But in reality, it will predict a lot more, in a lot more steps. It will predict sentences in maybe 100 steps, 100 iterations, every time masking some of the predicted tokens back and then predicting them again. So this paper's figured out it doesn't actually need so many steps. It doesn't need it. Instead, let the model stop early when it's confident that it has the answer. So don't have it for 100 fixed steps. If it's confident at 20 steps, let it just end there. So how do we measure this confidence of the model? So for each of these places, for example, U, it will take entire vocabulary of all possible tokens and assign probability for how likely is each token to be here at this spot. This is how it already works. This is the architecture that's current. This is not from the paper. This is how it works. For each place, it just assigns a probability for every possible token to be at that place, at that mask. And to know if model is confident, what they do in this paper, they check the probability of the most confident, highest probability token versus second highest probability. If the gap is large between first and second, then model is very confident that that first token is there. It has a lot higher probability. But what they do is to decide to early stop entire process. They take average confidence for all of the tokens. And if the average confidence, average distance between first and second most probable tokens is high on average, above some threshold, then they stop the generation process. And it maybe reduces their time by a lot, maybe 2 times, 3 times, or 75%. Or so when the average confidence is high enough, confidence gap is higher than threshold, ProFET, this mechanism makes the call to stop. And they just take whatever the current generation is and they make it as the final. And next, we will just go step by step, like reading this from the beginning, but you already understand the situation. But now we'll just go step by step, like summarizing the paper. The core problem with diffusion language models. So we know that diffusion models start with a sequence of mask tokens and iteratively refine them in parallel until a coherent sentence emerges. Think of it like a sculptor starting with a block of stone and gradually carving out the final statue. The problem, while diffusion language models have the potential to be faster because they can decode many tokens at once, parallel decoding, the paper points out 2 major issues that make them slower in practice. High computational cost. Their bidirectional nature, every token looks at every other token, is computationally expensive and doesn't easily support optimizations like KV caching. Many refinement steps. To get high quality text, they need to go through many rounds of prediction and remasking, which takes a lot of time. So they predict the mask token to a token, and then some of those tokens, for example, ones that were least confident, they mask them back, and then they predict them again, and then a chunk of those that are least confident mask them back, etc. The paper's goal is to tackle this second issue, reducing the number of refinement steps without sacrificing quality. New thing from the paper, early answer convergence. The authors discovered that in many cases, diffusion language models internally figure out the correct final answer very early in the decoding process, long before it completes all its scheduled refinement steps. The model's stop prediction for the answer tokens becomes correct and then stays correct for the rest of the decoding process. The remaining steps are essentially redundant, spent refining other parts of the text like the chain of thought or making tiny unnecessary adjustments. So the evidence, the authors ran experiments on benchmarks like GSM-8K, math problems, and general knowledge. They tracked when the model's internal prediction first matched the ground truth answer. On GSM-8K, using a technique called random remasking, 97% of correct answers had already emerged by the half point of the decoding process. And on MMLU it's 99%. This discovery proves that there is a massive amount of wasted computation in standard DLM decoding. The model knows the answer, but it's forced to keep working. The solution: ProFET and early commit decoding. Based on the discovery of early answer convergence, the authors propose a new training-free decoding strategy. It's called ProFET. ProFET is not a new model, but an intelligent algorithm or paradigm for decoding. Its job is to monitor the model's confidence during the refinement process and decide the optimal moment to stop early. The core mechanism is called early commit decoding. So instead of running for a fixed number of steps, for example 50, this is the action of stopping the process early and generating all remaining mask tokens in one final shot. At each step, ProFET asks, is the model confident enough in its answer right now? If the answer is yes, it triggers the early commit, saving all the remaining steps. This is visualized perfectly in figure 3. Saving means like not redundantly doing all of the remaining steps. So how does ProFET decide when to stop? The crucial question: how does ProFET measure the model's confidence to make this early commit decision? It uses a simple but powerful metric. New thing from the paper: confidence gap. For any token position, the model outputs scores, logits, for every word in its vocabulary. The confidence gap is the difference between the score of the first highest ranked token and the second highest ranked token. So, for every position, you just check the highest probability token, its score, its confidence, and the second highest, and so the gap between those two. A large gap means the model is very certain about its top choice. Small gap means model is uncertain, as the second best option is a close competitor. ProFET calculates the average confidence gap across the tokens in the expected answer region. It then compares this average gap to a threshold. Dynamic threshold. ProFET is smart about this. The threshold isn't fixed. Early in decoding, the threshold is set very high. ProFET is risk averse and will only stop if the model is extremely confident. Later in decoding, the threshold gets lower. ProFET becomes more risk tolerant because the potential time savings are smaller and the model's predictions are more stable. Triggering the commit: if the average confidence gap is more or equal to threshold, the ProFET stops the iterative process and performs the early commit decoding. So the ProFET makes a single decision to stop for entire remaining answer at once, not token by token. The setup: the model starts with a sequence full of mask tokens where the answer should be. The capital of friends is, and then 5 mask tokens. The refinement loop: in each step, the model makes predictions for all the masks. Step 1, prediction, let's say PARUS, and then in the step 2 it makes here I, so this is more confident, and here it would be uncertain, here it would be more confident in the step 2. In the step 2 it's Paris. ProFET's check, the global confidence assessment. After each step, ProFET doesn't look at the confidence for just the first mask. It calculates the average confidence gap across all the tokens in the answer region, so all 5 tokens. The average confidence gap. Is the model on average very sure that P is better than any other letter in the first spot, A for second, R for third, and so on? The early commit trigger: when this average confidence is high enough, confidence gap is higher than threshold, ProFET makes the call. The final action: ProFET tells the model stop refining. Take your current best prediction for every remaining mass token and finalize them all right now. The loop terminates and the final answer is generated in one shot. So check out other videos on my channel and join my Discord, and that's gonna be it for this time.